Hi, hello friends. Welcome to the today's session. Welcome to Unacademy and welcome to Srinivasarao Sir classes. In this class, we are going to learn the second part of error detection course, that is a cyclic redundancy checker and checksum. Before entering into the details, let us all say our anthem: crack GATE and ESE with India's largest learning platform, none other than Unacademy. Get Plus subscription and access unlimited live and recorded lectures from India's topmost educators. So Unacademy has created a good online platform which brought all the educators and the dedicated students on a single roof. So you and me are one roof with the help of Unacademy. So get the subscription of Unacademy and enjoy the benefits which are offering by Unacademy, like a live classes, live quizzes, mock sessions, and a guidance program. All are there which are beneficial to student members. My dear friends, myself is Srinivasarao Sir, having more than 15 years of experience at the GATE with the various subjects. I also had industry experience as a admin side, database side, and system analyst side. So I also had good certifications in the respective areas too. And throughout my journey of GATE, I taught in many premium academies with a high success rate. Many of my students got completed their post graduation from premium institution just by clearing a prestigious competitive examination called GATE. So if you prepare for GATE, it is a one examination can give you many benefits, that it is very easy to you to crack your campus placement and very easy to you to enter into public sector undertakings and many other benefits. So my dear friends, immediately you take the admission into an academy and get the benefits which are offering by an academy. There are two kinds of subscriptions. So one is a 12 month, the other one 24 months. If you opt for 12-month subscription, the current fourth year students can opt for this. Then you are going to get a maximized discount by using my referral code. Please use my referral code to get admission into an academy. So therefore you will be tagged to me. I can able to give you guidance to you. And the second kind of is 24 months subscription. The first and the second, third, fourth year students can opt for this. On this also you are having a maximized concession by using my referral code. So my dear friends, if you are first, second, third and fourth year student, you start your GATE training today itself, so that it will be very easier at the time of GATE examination. So let's crack GATE CSC is our YouTube channel. Subscribe our YouTube channel. Hit the bell icon for notifications and use my referral code to get the admission into Unacademy. Well friends, we will start our lecture. The lecture based on cyclic redundancy checker and checksum. These are the two advanced techniques. Right now we are all using cyclic redundancy checker. So in many kind of application, and DLL also is following cyclic redundancy checker. So what is a cyclic redundancy checker? We try to add redundancy bits in the form of a cycle till you get the reminder. It is based on modulo 2 division, which is nothing but we don't consider a carry, and it is based on binary division. It is also called as a binary division. Now what are the characteristics of your CRC, cyclic redundancy checker, which is nothing but it detects all single bit errors as long as you are having this kind of polynomial representation of your CRC generator. So it also can detect double bit errors as long as your CRC generator has at least three items, three elements you can say. So any odd number of errors can be detected whenever you are having your CRC generator has x plus 1. So 1 plus x is your factor to your CRC generator. So CRC 32 right now we are using, which is nothing but 32 bits. 32 bits binary division we are doing. So it is going to detect any kind of errors. So CRC32 can detect any kind of errors, which can be a odd length, which can be a even length, we don't mind. So there was one of the limitation, especially in a parity checker, that it can able to detect only odd bits, not a even bits position. That's why we have got one advanced strategy which is trying to detect a odd length as well as a even length. So you want to find out even length errors as well as odd length errors, please use your CRC32, which is following one of the good 32 bits combination of polynomial. So if you are using that CRC, that is a 1 plus x or x plus 1 CRC generator, then you are going to see that odd number of bits can be detected. So if I am using a 1 plus x, or if I am using x plus 1 as your CRC generator, it can able to detect a odd number of odd bit length of errors. But it is not providing any kind of assurance to detect the even length of errors. Again, that is a big problem. That's why to detect your odd length of errors and even length of errors, better you follow the latest CRC32. So we are using especially in CSMA and Ethernet, fiber distributed data interface, and ATM. And CRC CCITT is using currently in HDLC frame format. Well, my dear friends, so what is the process of your CRC? So please listen start of the class to end of the class, because I am going to provide why you need to take one x plus 1 at least, so that it is going to detect odd length of errors. Please wait and observe carefully. So what is a cyclic redundancy process at the sender side? So E is going to consider that M of x, and your CRC generator is your C of x, and your M of x is divisible by C of x. And before you start performing division is nothing but we are performing modulo 2 division, which is nothing but indirectly you are doing XOR operation. So before you perform XOR operation, add n minus 1 0 bits to your M of x. So what is the meaning of your n? Your n is nothing but your degree. So number of elements you are having in your CRC. So therefore those many number of bits supposed to 0 bits is supposed to add it to your M of x. So we are performing XOR operation, and the last n minus bits from your last reminder is your checksum only. So sender will send a frame consist of a code word. The code word consists of few important things. One is your actual message, the other one your cyclic redundancy checker. What is the idea? So whenever you are having a message here, before you perform your division XOR operation, we are trying to append zeros up to n minus 1 bits, or you can say that up to degree of your polynomial, anything is the same. And I am going to perform on this. The what? XOR operation, or you can say that modulo 2 division. And finally you are going to get a CRC. That CRC, how you are going to send the data to the receiver? Here anyhow we are going to send the data to the receiver, your message, and you are going to send your CRC. In place of this, we are trying to append these zeros. We are trying to eliminate those zeros just by replacing your CRC. So now in place of these zeros, I am just attaching your CRC to that. Finally, the sender is going to transmit here to the receiver a message which consists of what? CRC2. So this CRC number of bits are equivalent to number of bits you appended in it at the time of before you start your binary division. So therefore, the CRC whatever you got. So after performing modulo 2 division, you are going to get a CRC. So that CRC we are going to place exactly this position where you have appended your zeros. And finally you got a code word. Your code word consists of your original message and now the replaced CRC. So both together we are sending to the receiver. So receiver is going to perform a recomputation of your CRC, and there are two values is supposed to get in your reminder. You can call it as a syndrome, or you can call it as a final reminder value. If your final reminder value at the receiver is non-zero, then it is error. If final reminder value is a 0, then I can say that no errors during data transmission. Now if you look at CRC process at the receiver side, so once a code word received by the receiver, what a code word? The code word consists of your original message plus the replaced CRC in place of your appended bits. Now again he is trying to perform XOR operation, which is nothing but modulo 2 division or binary division. So if your reminder is a 0, then no errors in your data frame. Otherwise, if your reminder is a non-zero, then you can say that the frame contains what? Errors. So let us see the process. For example, so it is a 100 and 100, and your CRC generator is a 1011. So at least you're supposed to have, according to the characteristics, if you observe carefully, at least you're supposed to have minimum of 2 elements. Maximum, that is up to you, how many you can able to have. I will show you the guarantee conditions, what are you are going to require. So minimum your CRC generator requires, please understand, minimum your CRC generator requires at least 2 elements. So minimum you're supposed to satisfy 2 elements to detect at least an error, single bit error. But you observe here carefully. So if your CRC do not have minimum of 2 elements, it cannot able to detect any kind of error. That is the reason. Please understand why there is a requirement of minimum of 2 elements. If you are not providing a minimum of 2 elements, it cannot able to detect any kind of error. You are not eligible to do what? Your CRC process. You want to perform a CRC process, there is a requirement of a minimum of 2 elements and maximum can be anything. So according to this example, your CRC generator has a 4 elements. Observe carefully. So 4 elements are there. This is a 1 element and a second element, third element and a fourth element. Any number of elements you can have, but according to CRC 32, you're supposed to have 32 bits. That's the meaning of CRC 32. Now if I'm saying here, so what is your exactly your CRC generator is? It's supposed to be in the form of a polynomial I'm writing x power 0, x power 1 and x power 2 and x power 3 and it's so on. As I'm having a 4 elements here, so first element, second element, third element and 4 element, therefore I'm using like this 1011. This is what is the meaning of your representation of polynomial into binary, and this is your polynomial representation of your binary bits 1011. So my dear friends, your CRC generator can be represented in the form of your algebra expression, that is nothing but polynomial form, which is of x cube plus x square plus x plus 1. Otherwise you can also write in the form of what? Binary. So you can also write like this. So anyhow, he has mentioned to us the 4 elements is supposed to have. Therefore, it guaranteely detect errors. Why? Because you're satisfying the greater than is equal to 2 elements. So what is the rule? Your whatever you say, that if I am saying that my CRC generator in the form of x, if I am saying that this is my x, then it should not be divisible by x and it should be divisible by 1 plus x. Why? X means you cannot, if it is divisible by x, you cannot detect any kind of error. I will show you proofs. If it is divisible by 1 plus x, then it can able to detect odd length of error. Therefore, you're supposed to maintain minimum of 2 elements in your CRC generator. Now let us continue how you can able to identify your data is 100 and 100 and your polynomial is mentioned in the binary 1011. The formation also I shown you how you got 1011. It is in the form of x power 0, x power 1, x power 2 and x power 3. Now let us see, my dear friends. Let us start XOR operation or modulo 2 division. Before you start division, what I said, you need to inject 0 bits. This is a mandatory. That's what is the meaning of what? A redundancy. Adding of redundancy bit in a cyclic manner. First in one cyclic 1 bit, second bit, third cyclic third bit. So how many zeros you need to add? As your CRC generator has got 4 elements, I can able to inject n minus 1 zeros. That's nothing but triple zero. Otherwise, you see here, your degree of your polynomial is 3. Please understand. Your degree of polynomial is 3. Therefore, I can able to attach 3 zeros. This way is also correct. That way is also correct. If your CRC generator has got 4 elements, then I can able to do n minus 1 redundant bits. Otherwise, if your CRC generator has got degree is 3, then directly I can able to inject 3 0 bits. Now let us start. Your MSB is a 1, so I can start with 1 only. As I am taking a 4-bit XOR operation, so therefore 1 with a 1011, then it is a 1011. Now XOR operation, this is give you 0, this will give you 1, this will give you 0, this will give you 0. Up and down same means it is a 0, otherwise non-zero. That's the meaning of XOR operation. Now most recent 0 you cancel. This is your most recent 0, you can cancel. There are 2 ways to do this problem. I will show. This is a one method I am following. And next one more bit you drop here. Now your MSB is a 0, so I am taking a 0 here. Therefore 0, 0, 0, 0. Now I got 0 here, 1 here, 0 here. This you can cancel because that was your result MSB. Now one more 0, you just drop it. Now your MSB is with 1, so I can start with 1. I am adding a 1 here, so 1 0 1 1. Now it is a 1 1 0 0. Cancel this 0 MSB. Now you drop once again 0. Now your MSB is got 0, so I am taking here 0 only, which is nothing but 4 zeros. Now you got once again 0 here, 1 here, 1 here, and 0 here. Now you start continue dropping a 1 more 0. Your MSB is a 1, therefore I am attaching with a 1, and it is a 1 0 1 1. So you got 1 1 1 and MSB 0 you can cancel. So 1 more 0 I am dropping here. So it is a 1 1 1 0. Your MSB is a 1 here, so I can perform with the 1, otherwise 0. So 1 0 1 1. So you got one answer. What is your answer? Finally you got the 1 here, 0 here, 1 here, 0 here. So you have to stop your work and take your remainder part from your right to left to 3 bits because you have added 3 bits here. So your degree of your polynomial is going to be your CRC only. Your degree of your polynomial is a 3, which is nothing but x cube plus x square plus x plus 1. So your degree of polynomial is 3. So I'm going to take 3 bits as your cyclic redundancy check. This we are going to replace into this. So once you replace, the sender got constructed a code word. The code word is in the form of what? 100 100. This is your m of x, and we are also going to attach your CRC, which is nothing but error detection code. You got this is 10. The same you can also perform. The same you can also perform in different way. Is that? Let us see. So if I am taking the same example here, so 100 100, and 3 bits are appended as zeros. Your polynomial is given as 1011. Now you start this, so MSB is a 1. I am starting. So 1011. So it is a 1100. So I can start directly from your MSB 1 only. So now 2 zeros you drop, and your MSB 1 I am taking with a 1. So it is a 1011. So 1110. So you can start with your MSB1. So I'm dropping a 0 here as 1 is there. So I can able to perform 1011. It is a 1 and 0, 1 and 0. This you can cancel. And this is one more 0 I drop. So I can perform with a 1 because your MSB is a 1. So 1011. Now you got 1000. So now you observe carefully. So I can cancel this and you can able to drop one more and continue this. So this is how you also can able to generate your CRC. This is a second model. Directly you can cancel all the zeros, still your MSB is a 1 and you can continue. Now there is an important point. Why to take a minimum x plus 1 as your CRC generator? That we will see now. So before discussing that, let us see that how the receiver can able to detect the error if at all he got some corrupted bits in the frame. So I'm showing you that the sender is sending. Sender sends as 100, 100 and 101 and receiver receives. If receiver receives as 100 and 101 with the 101. So we want to find out, is there any error or not? Find error is there or not. So we will do once again the same process. What is that? The divisor is going to be, the polynomial is going to be shared by your sender. So use the same polynomial or CRC generator. Your CRC generator is a 1011. I'm going to do the same process at the reverse side. So MSB is a 1. I'm starting with a 1. So 1011. So 0 here, 1 here, 0 here, 0 here. Now we drop one more 0 here. As your MSB is 0, I'm starting with the 0 here. So 1, 2, 3, 4. And you got 0 here, 0 here, 1 here. This 0 you can cancel as it is MSB. And drop one more 1 to perform equivalent binary division. So as your MSB is a 1, I can start with a 1 here. So 1011. So yours is 0, 1, 0, 0. Now I can carry forward still. So 1 is given there. So you got next here 0, 1, 0, 1. And your polynomial is 1011. And still you are having a 0, 1 here. So as your MSB is 0, as your MSB is 0, I am starting with continue from there. 1, 2, 3, 4. And you got 101 and this 0 you can cancel and this 0. So as your MSB 1 in this, so 1 is added. So 1011. So 1000. Now you can cancel it. So one more bit is left there, that is a 1. Now it is 0, so I need to perform with the 0. So 0, 0, 0, 0. You are going to get a non-zero here. This 0 you can cancel 0, 1, 1. Therefore, you see, even you try to do that, you are not going to get 0. If your syndrome is 0, at the final remainder is 0, then you can say that no errors. But here your final value is a non-zero. It is a non-zero. Then I can say that there is an error. So where is error? By comparing sender 1 and receiver 1, you can understand this is arrived pakka and same and same and same and same. This is your error. Because of this error, the receiver could able to detect that there is an error because he performed a reverse operation with your cyclic redundancy checker. Now, observe carefully. So this is one of your previous gate question, that is 11001001. He has given xq plus 1. You check that how many elements are there in your CRC. This is very important. CRC generator whether you are having greater than is equal to 2 or not. CRC generated elements. Yes, exactly. I have got greater than is equal to 2 elements because it consists of x cube plus 1 is nothing but, which is further derived in the form of x cube plus x square plus x plus 1. That is the formation of your polynomial. So I have got 1, 2, 3, 4 elements in this. So therefore your condition is satisfied. What is your condition? Your CRC generator at least must have minimum of 2 elements. So I have got 4 elements, no problem whatsoever. Why to have minimum of 2 elements? Please wait and observe. Why not to have lesser than is equal to 2, less than 2 elements? What is the problem? I will show you. Please observe carefully. In this example, I got a 4 elements. Therefore, 3 zeros I can able to append it at LSB of your message X. So your message is 11001001. 11001001. And you know that we need to append your degree of polynomial is 3, otherwise 4 elements are there. So I need to inject n minus 10 bits. I have got injected. And what is your polynomial? Your polynomial is x cube is on, x square and x is off. Observe carefully. X cube is on and x square is off and x is off and 1 is on. So I can write in this format. Therefore it is 1001 is your polynomial. 1001. Now we will start our work. Your m of x consists of, this is your m of x and this is your redundant bits, redundancy. So we will start. This consists of 1, so I am starting with a 1. So 1001. So 1010. And next I am having a 1 here. So your MSB is a 1. I will start with a 1. So 1001. 0100. So I can start from here. Otherwise you can cancel those zeros, I don't mind, but I am doing as a process. As your MSB is a 0, I am starting with 0 once again. So 1, 2, 3, 4, 0, 0, 1, 0. This 0 you can cancel and this 0 you can drop it. As your MSB is a 1, so I can start 1001 and this is a 1000. Now I can continue. So next I am going to drop 0. So as it is a 0, 0, 0, 0, 0. You got 0, 0, 1, 0. You can cancel it. Next I am dropping a 1 more 0. As here 0 is there, again I am performing the 4 zeros. So finally you got 0, 1, 0. This 0 you can cancel. Next you drop 1 more 0. As your MSB is a 1, I can perform with this 1001 and you got finally 100 and 0. So last 3 bits from rightmost to right towards to left, your n minus 1 bits or 3 bits is your CRC. Now you got error detection code as a 001. This we are going to append. This we are going to keep it in this place. So finally your code word is nothing but 110010010001. This is going to be transmitted from sender to the. Next we have now we are going to see that why there is a requirement of the polynomial generator should have following properties. What are the properties? The properties are, it should have at least two terms, and the coefficients of the form x power 0 should be 1, and it should not be divisible by x, and it should be divisible by x plus 1, because x plus 1 is a factor of your g of x. Here x is nothing but your CRC generator. Now let us see, if I am taking different assumptions I am following. What are the different assumptions I am following? If I am taking my CRC generator is a 1, please observe, I am taking only one bit as your CRC generator. What will happen? If I am taking my CRC polynomial as a 1, your CRC generator is equal to 1, which means how many zeros I need to append to your data? Your m of x is equal to 1011. Now you see how many zeros I need to append. This is very important. How many zeros I need to append? Your CRC generator has got only one element. One element is given. So how many zeros you need to append? N minus 1 zeros you need to append. But your elements are having only one. So n minus 1. 1 minus 1 is nothing but what? 0 bits you need to append. Therefore, I cannot process further because the degree of CRC generator is a 1. So you cannot add any redundant bits in the data. So algorithm cannot proceed further. That's why you cannot take a single element. Observe carefully. You cannot take a single element. So that's why you're supposed to have minimum of two terms. That's what the rule I have given you. What is the rule? Minimum of two terms is supposed to have. Why? If you take a one term, this is the problem. What is that? You cannot append any kind of zeros to your LSB to your message. So here, according to that, zeros to append means what? Zeros to append. No zeros can be appended to your matrix. That's why this is wrong CRC generator. Invalid CRC generator. This is. It's an important point. So if I am taking x is nothing but if I am taking x is equal to 1, let us say. So your data is a 1011 and I am taking this time CRC generator is equal to x. So how can you write this x? This x has got two terms. So what are the two terms? X power 0 plus x power 1. So this can be represented in this polynomial expression. How you can write this? X power 1, that means 1 into x power 1 plus 0 into x power 0. So if I am taking those coefficients 1 and 0, you got two terms now. So your CRC polynomial, according to the previous CRC generator, is 1 0. Now you got two elements. Plus. So when you got two elements, I can say that this is a good CRC generator. Valid CRC generator. Later we will see that whether it can able to detect errors or not. First, according to this particular point, I can say that it is a valid CRC generator or good CRC generator because I can add some zeros here. That's the meaning. I can add zeros here. How many elements are there? Two elements are there. So to my data, I can add m of x plus your redundancy you need to add. So how many redundancy bits you need to add? N minus 1 bits you need to add. So your n is nothing but the two elements. At least I can add 0. 0 to start your algorithm. That's why you see that minimum two elements required in order to perform CRC. That's why don't take one element. Your CRC generator elements is supposed to be 2 or greater. It can be 2 or greater. It can be. Now this is a second one. Please understand. This is the first one. Why we cannot have a single element as your CRC generator? And the second one. So by having a two elements, I'm taking x. X is nothing but I can able to put it in this polynomial expression, which is nothing but x power 0 plus, and to left hand side x power 1, x power 2, x power 3, and so on. So it is a 1 into x power 1 and 0 into x power 0. Therefore, I got two elements in this. So m of x plus your n minus 1 redundancy bits. Here n is equal to 2 you got. Therefore, 1, 0 I can able to add. I can able to process my work. Now let us see. I will study and continue this. What is your CRC with this example? I am saying that my m of x is equal to 1011 and your polynomial you got in the form of binary, which is a 1 0. Now let us start our work. So 1 0 1 1. How many zeros I need to add? You have got two elements, so I am adding 1 0 only, n minus 1 redundancy. Now let us start our work with the 1 0. So as your MSB1, I am working with the 1. So 1 0. So 2-bit combination, it is a 0 and it is 0. We eliminate this. You drop this one. So your MSB is a 0. I am working with 0. It is a 0 0. Now you got the 0, you can cancel 1. This one I am carry forwarding. So as your MSB is a 1, I am taking a 1. So it is a 1 0. So it is a 1 and this 0. This 0 you can cancel. Next I am dropping this 0. As your MSB is a 1, I can use 1. So it is a 1 0. So now you observe, my dear friends. So this is how it happens. So now you are going to send your data in the form of what? According to this fashion. What is that? Your data is a 1011 and you got something like a 0. You do the same process at the reverse side by doing some kind of wrong manipulation. So some people are asking me do once again. So let me show you once again here. So see your MSB only. One zero one one and 0 is appended. Your polynomial is 1 0. I'm starting with a 1. So look at 1 0 here. Drop this one. Your MSB is 0. Work with the 0. 0 0 0 1. You drop 1 here. Your MSB is a 1. Take it here. 1 0. And it is a 0 1. Cancel the 0. And your MSB is a 1. Do it here. 1 0. Now you observe carefully. What is that? This is what is happened at the sender side. And what the receiver is doing and what you are sending to the receiver. If sender sends, please observe. sender sends 1011 is your data and 0 as your EDC to the receiver. So receiver is trying to perform same operation by taking this EDC. Now what is happening at the receiver side? 10110. Now if you perform once again with your 10110, so now here what happened? Again we do the same process. So you are going to get finally 0. So we will understand that no errors in this. But if sender sends, for example, the sender sends as he is sending your data 1011 is with your CRC 0. Now you see this is transmitted in the media. This is transmitted in the media as 10100. Now receiver is going to perform the same operation. 10 is your polynomial. So 1010 and 0. Now we started doing. So your MSB is a 1. So I am taking here 10. It is a 00. Cancel this 0. And you add 1 here. Your MSB is a 0. So I am performing the 0. This 00, 01. And drop this 0. Your MSB is a 1, 1, 10. It is a 00. And your MSB 1, again 00. Finally you got 0. Is it detected any error? Is it detected any error? So we will say no. So why we will say no? Because you please observe that 1011 what the sender has been transmitted, but receiver has received 1010. This is exactly an error, but it cannot able to detect it. That's why you want to detect an error. There is a requirement of what? Please understand, my dear friend. So if I am taking that my CRC generator is X. If my CRC generator is X, its coefficients are 10 like the previous example. Even though you are sending a wrong data, or if the data is corrupted due to the noisy, why we are getting errors? Due to the noisy or due to the attenuation. There may be a chance of errors, but this is not going to detect any kind of error at the receiver. We already seen the proof. What is that? The above CRC generator cannot detect any error at the receiver side. So therefore, this is not at all a valid CRC generator. So far we have discussed, if your CRC generator is a 1, what will happen? Only one element. So you cannot append any zeros. If your CRC generator has 2 elements, that is nothing but X. This X we have represented in the form of 10. Then what is the problem? This is also invalid and this is also invalid, because this is not at all detecting any kind of error, not detect error. That's why we want to see a good polynomial which can able to detect the error. So according to this is a valid only. I can understand that this is a valid CRC generator. Why? Because it has got 2 elements. So therefore I can able to append 10 bit to your data. So it is a valid generator, but it is not a good CRC generator, because even though errors are there, it cannot able to detect any errors. I already shown you the proof. So this is how, even though there is an error is occurred, it cannot able to detect any error. So that's why you need to change your CRC generator to at least to X plus 1. So X plus 1 is your one of the good CRC generator which can able to detect the errors. Let me show you. So our next CRC generator I am extending to x plus 1. First we take x, first we take 1, then we upgrade it to x, then we are adding x plus 1. Now what will happen? If you are saying that your CRC generator is x plus 1, then I can write its polynomial in the form of 1 into your x power 0 and 1 into your x power 1. So what are your coefficients? Your coefficients are 1, 1. Is it eligible as a good valid CRC generator? Yes, of course. Why? Your CRC generator, you are having at least two elements greater than is equal to 2. It is a possible. Hence, this is a valid CRC generator. No doubt. Valid CRC generator this is. But let us see whether can it able to detect errors or not. According to the previous, it is also valid CRC generator only, but it is not a good CRC generator because it unable to detect any kind of errors. It is not a good CRC generator. That's why your completely CRC depends on your generator only. So I am taking one more CRC generator, which is nothing but x plus 1. I can able to write in the form of double 1. So what is your degree of your polynomial? Your degree of your polynomial is a 1. Otherwise there are two elements are there in your polynomial. So I can able to append a 1 0 bit to you. So only 1 0 bit can be appended to your data before start performing for binary division. So let us see the same data 1011 with the 1 1. So 1011 and you can append n minus 1 0 bits here. Now you start with the 1 1. So as your MSB is a 1, I can start with a 1. It is a 1 1. So 1 and 0 I can cancel and 1 bit you drop. So MSB 1 I am doing it a 1. It is a 1 1 0 0. You drop one more bit. So as it is a 0, I am performing the 0. It is a 0 0 0 1 and you have got a 0 here. So as your MSB is a 1, I am taking a 1 1 1 then 0 1. So as this 1 is appended because your n minus 1 bits are your CRC. Now the sender is transmitting your data in the form of your M of x plus your CRC. CRC is nothing but your EDC only. So what is your M of x? 1011 plus your CRC is 1. If receiver receives in different format, let us say if receiver receives received frame as 1010 and with 1. Now he is asking find errors are there or not. Is this CRC generator can able to find error or not? So we will do the same process 10101 and your polynomial is going to be shared in the header which is nothing but double 1. So I am taking MSB1, it is the 1 1 1, so 1 and 0. Now this is your 1, so MSB1 1 1 0 0. Cancel this 0 and this is your 0. Again MSB 0 double 0 0 0. Cancel this 0 and drop this 1. This is a 0 0 0. Now you got 0 1. So cancel this. So you got non-zero. So when you get a non-zero, I can understand that there is an error. See, my dear friends, by using x, is your polynomial. That means x is nothing but I have defined is in the form of 1 0. It is not detecting any errors. Not detecting any errors. That's why we have changed the polynomial to 1 plus x. So we have changed the polynomial to x plus 1 or 1 plus x. Now it is written in the form of double 1 can detect error. So let us see, I have changed only one bit, so it able to identify the error. Now let me change the 2 bits positions. If receiver receives frame as, please observe, what is our old format? 1010. So our original data is 1011. So I'm going to change 2 bits corruption. So 1000 we will send 1000 and 1 is your CRC. Now let us see that whether will it able to find errors or not. Our question is that this and this is wrongly arrived at the receiver side. So he is doing a once again. So your polynomial is 1 1. Your data is a 1000. This is 1. As your MSB is a 1, I am starting with a 1. It is a double 1. So 1 here, 0 cancel. And a 0 here, 1 here, 1 1. So 1 and 0 cancel this. And drop this 0. So 1 here, 1 0. It is 0 0. Cancel this. And this is your 1. Please understand. So as I am doing with what? 0. So it is a 0 0 and you got 1. So this is how you can able to decide that. So when you are having a concept of x plus 1, I can able to detect errors. So my dear friends, so these are the CRC generators right now we are using. That if you are using CRC8, this is the format. If you are using CRC10, this is the format. If you are using CRC12, this is the format. And right now we are using CRC32, especially in your carrier sense multiple access as well as in Ethernet. We are following this, and your HDLC is following this format. So now let us see the last technique, that is called checksum. So it is a very simple technique. Why it is a simple technique? It is used by higher layer protocols like Internet Protocol and TCP and UDP. They are following checksum. So it is based on one's complement addition. It detects errors, even length as well as odd length. So what is the disadvantage? Disadvantage is you can have a maximum of 16-bit position only, not more than that. So your checksum maximum limit is only 16 bits. So this is one of the limitation. So let us do what is the process. It is completely based on one's complement addition. Let us see. If data is 7, 6, 12, 11, then he is asking find checksum. So your checksum is nothing but do the first sum among them. Some given numbers are 36. So sender is going to do by injecting negative of it, complement, negative of the 36, it is a minus 36. So sender sends data 7, 6, 12, 11, minus 36. General idea I am saying. So when this is sent by the sender, and if receiver receives in the same format, then your positive 36 and minus 36, you are going to get a what? 0. I confirm that, no errors. If any data is corrupted, instead of 7 some number, instead of 6 some number, instead of 12 some number, instead of 11 some number, then you can say that it is not going to be exactly 0, it is going to be non-zero. Whenever you say that non-zero, it is a concept called what? Error. 0 means no error. So how are you going to do this? This you can able to do in such a way. So receiver received a frame as like this, and after checksum, if the remainder is 0, then no errors, else errors. Let us do in our regular term. First step is, by calculating your sum value, you got 36. Write your 36 in your binary, which is nothing but 100 is your binary. Observe carefully, because so this is a 1, 2, 4, 8, 16, 32. 32 is on and 4 is on, so your value is 36. Now you observe, I need to do wrapping and finding a checksum. How to do wrapping? Because I am doing a 4-bit calculation here. So therefore you have got a carry here. So what I am going to do, your 1, 0 and 0, 1, 0. 4-bit manipulation it is. This 1, 0 whatever is there, we are appending to this. Now you got finally your value is 0, 1, 1, 0, which is nothing but 6. This is your, so which is nothing but 6 there. That we are going to complement. So complementing value is, these bits are being complemented now. 1, 0, 1, which is nothing but 8 plus 1, it is a 9. So these are the steps I have given. What are the steps? Rapid sum is 4-bit combination is a 6, that is a 0, 1, 1, 0, and it is a complemented as a 9. Now sender sends this all together. What is that? 7, 6, 12, 11, and your checksum value. This is your checksum, that is a 9. All together, it is how much, my dear friends? 45. What the receiver is going to do? So receiver takes that 45 here. 45 is nothing but 7, 6, 12, 11, and your checksum value also. Now 45 if you write in binary, this is your 45 binary. So what I am going to do, I am trying to wrap it to 4-bit combination, because my data is only 4 digits only. So 4-bit combination I am writing. So when you write the 4-bit combination to do this, that is nothing but 1, 0 is your carry, 1, 1, 0, 1 is your. So this one we are trying to wrap here, 1, 0. Therefore you are going to get 1, 1, 1, 1, which is nothing but 15. And just you complement this, it is going to be 0, 0, 0. And I can say that there are no errors. This is how you can able to see that checksum is going to be done. I will show you how you can able to do in a binary formations. So let us see one example here. 4 frames I am transmitting. Same like the previous question only. This time I am going to write in the binary. Earlier it was in the decimal. So I am taking 4 frames. So 1100, 1100 is one of your data. And the second one is 1010, 1010, another data. Next one is 41 and 40 is another data. 1100, 0011 is another data. So to this we want to find out what? Once complement addition, then how you are going to get a checksum. Let us see. So it is a 1 here, observe carefully. So 1 and 1, 1 plus 1 is nothing but a 2. 2 means I can write in the form of 1, 0. So 0 is here and 1 is here. Now 1, 2, 2 again you got 2. So 0 is here and 1 is here. So 1, 2, 3. 3 means I can write in the form of 1, 1. So 1 is here and 1 is here. Now it is a 1, 2. 2 means 1, 0. I can write here 0. I can write here 1. So 1, 2, 3. 3 means 1, 1. So 1 here and 1 here. So 1, 2, 3, 4. 4 is nothing but 100. Observe carefully. So 0 here. And after cancellation of 0, you got how much? 10. 10 is nothing but 2 only. So you got 2 here. So 2 plus 1, 3, 4, 5, 6. 6 is nothing but 0, 1, 1, 0. So write that 0 here. And the rest is a what? 0, 1, 1. Now you add this into this. Now you got finally, what is your value? So 0 here, 1 here, 0 here, 1 here, 0 here, 1 here, 0 here, 0 here. So you got sum. So to this sum we want to do complement. So once you do the complement, it is a double 1, 0, 1, 0, 1, 0, 1. This is your checksum. So now the sender is going to send all your 32 bits plus these 8 bits together, because 8-bit checksum we are taking because your given data is also in the form of 8-bit only. So double 1, 0, 1 and 1, double 1, 0, 1 and next one 0, 1 and 0, 1. Now what is the process at the receiver side? If receiver receives same data without any data bits corrupted, if receiver receives same data bits with the EDC, error detection code, as checksum. Now let us take all of them and bunch together. 1 1 0 0 1 1 0 0. And next one is 1 0 1 0 1 0 1 0. And next one is 4 1s 4 zeros. Next one is 1 1 0 0 0 0 1 1. And next one is your checksum 1 1 0 1 0 1 0 1. So all are pakka arrived. So we want to see 0 here. So all are pakka arrived without any errors. So we want to see that 0 there. Let us see 0 is coming or not. So I am saying that 1 1 2. 2 is nothing but 1 0. So left is a 1. So 1 2 3. 3 is nothing but double 1. So 1 cancel, 1 is the carry. So 1 2 3. Same. So 1 2 3. Same. So 1 2 3. Same. 1 2 3. Again same. 1 2 3 4 5. 5 is nothing but 101. This is your 5 format in the binary. So take your 1 and take out 1 0. 1 0 is nothing but 2. So 3 4 5 6 7. 7, how will you write? Triple 1. So once you do triple 1, so you append to that. So once you append, then you are going to see that all ones should come. Then after that we are going to see that complementation is all 0. So this is how we are trying to solve a concept of checksum. For example, my data is 1 0 0 0 1 1 0 0 and is asking it to find a checksum. Same story, simple formation. It is a universal calculation. 0, 0, 1, 0, 1. 1 you add it here. 0, 1, 0, 1. Just to complement this. Then we got 1, 0, 1, 0. This is your checksum. So now we will hand over this to the receiver side. So receiver is taking your data 1,000, 1100, 1010. So this is 0, 1, 1 and 111 means it is 311. This 1 you add here as a carry. So 1, 2, 3, 4. This is your reverse checksum and you complement this. Once you complement, you are going to get. So I want to give you a task to you. What is the difference between CRC and checksum? So CRC can detect any length of errors if you are using a good polynomial, and checksum also is going to do the same. But what is the difference between your CRC and checksum? So CRC is based on by performing binary division or XOR operations, and checksum is based on ones complement addition. So which is having more significance than others? So which is going to be the best one, CRC or checksum? That you tell me to comment. So this is how the CRC is the best than anybody. But checksum we are going to use in real-time calculation because it is open. When you are talking about the CRC, you need to share the polynomial CRC generator carefully. First, you need to develop the CRC generator so that it is going to detect any length of error at the other side. That's why calculation of the CRC generator is a mandatory. But in checksum, it is not like that. It's a very simple process. What is the process? Do the ones complement addition and send it to the other side. If any bits are corrupted, then it is going to see that a non-zero value. If no bits are corrected, we are going to see that what? Zeros. So this is how you can differentiate between checksum and CRC. And one more, which is going to detect even length and odd length, and checksum also can detect even length or odd length. Tell me in the chat box. So my task is to you, please do R&D. What is that R&D? I said that CRC can detect even length as well as odd length. My question is, can checksum detect even length and odd length errors or not? This is my task to tell me tomorrow's session. So CRC can detect, no doubt, even length and odd length errors also can be detected easily, which was not there in your parity, and that is rectified in CRC. But can the checksum also do the same? That you can able to detect even length errors and odd length errors? To tell me in the next class. Our next class session is Hamming distance. So this is your tomorrow's session, Hamming distance. Well, friends, so thank you for sparing your valuable time. So any doubts you can ask me now. So while doing a binary division, you can cut off 110. Otherwise, you can cancel up to your MSB1. You can able to do it. Zifa. So thank you all. So this is the task. Please tell me tomorrow. What is the task? Can checksum detect even length errors as well as odd length errors or not? You do one or two manipulations, then tell me whether will it able to detect or not. And one more task I want to give you. If you are capable, you do it. So I'm taking some data like 100 and 100. I want to say that my CRC polynomial is something like x plus 1. which is nothing but double 1. Now you tell me, does it detect even length errors? Does it detect even length errors? So this is my question. No doubt it can detect odd length errors. I'm saying that, does it detect even length errors or not? So we'll meet in the tomorrow session. Hi, hello friends. Welcome to the today's session. Welcome to Unacademy. In this session, we are going to learn about error detection codes, that is CRC and checksum. Before entering into the details, let us say our anthem, crack GATE and ESE with India's largest learning platform, none other than Unacademy. Get Plus subscription and access unlimited live and recorded lectures from India's topmost educators. About myself is Srinivasarao Sir, having more than 15 years of experience in the GATE, and throughout my journey of GATE, I taught in many premium academies, and many of my students got completed their post graduation from IITs, NITs, and central universities. So if you take the subscription in Academy, you're going to call it as a plus member or a prime member. By using my referral code, you're going to get a maximizer. There are two kinds of subscription. One is a 12 months, the other one is a 24 months. If you take a 12-month subscription, current fourth year students can opt, and 24-month subscription, second and third and fourth year students can opt. And the first year students also can able to start. My referral code is also eligible for 24 months and 12 month subscription. This is eligible for any kind of course. My dear friends, now we are going to look at into cyclic redundancy checker. So it is based on binary division. So whenever you talk about the binary division, so we are doing in the form of what? XOR operation in order to derive your CRC. So CRC characteristics are can able to detect a single bit errors, and CRC can also detect the burst errors. That is the power of CRC, which was not there in your parity base. So right now we are using the CRC 32 in CSMA and FDDI and ATM, and the CRC CCITT is used in HDLC. So now, before starting CRC, there is some important thing is that you need to see that what is the process at the center side. So the message is M of X and CRC generate is a C of X, and your M of X is divisible by C of X, which is nothing but XOR operation we are going to do. And before you start dividing, add n minus 1 zeros to your M of X. Your n is nothing but number of elements are in CRC generator. Therefore, my dear friends, just we do XOR operation and last n minus bits, the remainder is your CRC. So sender will send the frame consist of your M of X and the CRC, and this CRC is appended with your M of X. And the receiver side process is nothing but it is going to see that M of X and plus CRC. It is a performing XOR operation that side. So you see that if no data bits are corrupted, your remainder is 0. Otherwise, it's going to consist of some kind of errors. So according to that, I am taking this example. CRC generator is a 1011, and your data is a consist of 6 bits, and CRC generator is a 4 bits. That means what? 4 elements are there. So what are the elements are there in your CRC? So if it is the C of X, and your X consists of 4 elements, what are that? 1011. I can say that this is X power 0, this is X power 1, this is X power 2, this is X power 3. So your degree of your CRC is 3. So your polynomial Your polynomial is nothing but 1011. Now using that, we want to solve that calculation of CRC and all. Before calculation, let us see some important rules over here. The important rules are polynomial generator. So polynomial generator should have the following properties. What are the properties? It should have at least two terms, and the coefficient x power 0 should be 1. The mandatory rule, last one. And it should not be divisible by x, but must be divisible by x plus 1. This is important rule, because x plus 1 is a factor of your g of x. Now you look at, my dear friends, I'm taking a different permutation combination to choose your generator, CRC generator. I'm saying that according to this example, my C of x is nothing but your CRC generator. Your CRC generator, you are having a 1. Is it a valid CRC generator? Is it a valid CRC generator? We will say that no. Why no? Because your n is equal to here 1. So how many bits I need to append to your data? So your data is nothing but 1011, and I need to add n minus 10 bits. But here n is a 1, so 1 minus 1, 0 bits are not possible to append. 0 bits are not possible to append. That's why you observe carefully. This is not a valid CRC generator. That's why minimum your CRC generator requires a minimum of 2 elements. That means it's supposed to be greater than is equal to 2. But here your elements are 1, hence it is wrong. Now next example, I'm taking a minimum of 2 elements. So I'm taking x is nothing but your x I can able to write in this form 0 into x power 0, 1 into x power 1. So if I take your coefficients, they are 1, 0. Now you got n is equal to 2 elements. So when you say that n is equal to 2 elements, I can understand that the degree of the polynomial is a 1. So I can able to add at least 1 0 bits to that. So n minus 1 0 bits I can able to append to your m of x. So I say that my m of x is equal to 1011, and I can able to append what? 0 bits to that. Therefore, it is a valid CRC generator. I can write that it is a valid CRC generator because you have got at least 2 elements. Yes, there are 2 elements. So this is the reason you're supposed to maintain 2 elements. And now you need to see that this CRC generator is eligible to detect any kind of errors or not. We want to cross check whether this one is eligible to detect any errors or not with this following data. I'm taking our data is 1011, and I have had only 1 0 bit, and your polynomial is a 1 0. Now I'm talking your MSB is a 1, so I can do with the 1, so 1 0. Now 0 and 0 cancel this 0, and this one you write. Now your MSB is a 0, so I need to do with the 0. It is a 0 0, and 1 and 0, this 0 you can cancel. This 1 you drop it. As your MSB is 1, I can do with a 1. So there is a 1 into 1 0 is a 1 0, 1 and 0, and you cancel. And next you drop this, it's 1 0. So 1 0, as your MSB 1, I can write with a 1, 1 0. So you got your CRC as a 0. So I have transmitted this data. So due to some noisy, bits are corrupted. Due to some noisy, bits are corrupted. When bits are corrupted, they are being transmitted like this. How sender will send? Sender will send 1011 and your CRC. CRC is 0. That is appended to your n minus 1 position. Now I have transmitted, so receiver receives 1 0, 1 0 and 0. So as a human being, we can understand that this bit is corrupted. But let us see, CRC can detect errors or not using the same equation. So our polynomial is 1 0, as your MSB is a 1. So 1 0, 0 0, do this, and 1. As your MSB is 0, I will do with 0, 0 0, and 0 1. We cancel this and drop this 0. So as your MSB is a 1, so I got a 1. It is a what? 1 0. It is a 0 0. Cancel this 0. And this bit I have dropped. Now again your MSB is 0. I'm doing with 0. Again you got 0. Now 0 means no error. So there are two values. Here one condition we are going to have, that is called as your syndrome. So what is your condition? If your receiver side, your syndrome is, if receiver receives 0, then I can understand that no errors. If receiver receives a non-zero, if it is not equal to 0, I can say that it is error. But actually the bit is corrupted. This bit is corrupted. Actually sender sent like this, but receiver receives like this, but it unable to detect any error. That's why I can say that this one is a valid CRC generator, but it is not a good CRC generator. Not a good CRC generator. Why? Because it unable to detect any error. The above CRC generator cannot detect any error at the receiver side. So you need to change your CRC generator. If I am taking x plus 1, first I took 1, then I took x, now I am taking x plus 1. If I took x plus 1, what will happen? I can able to write your x plus 1 in this case. How? X power 0. 1 into x power 0 and 1 into x power 1. This was the rule I already gave you. Now the coefficients are 1 and 1. So here also your n is equal to 2. So number of elements are at least greater than is equal to 2. It is a good polynomial, no doubt. Now we want to see that whether can it able to detect errors or not. Let us cross check once again. So 1 0 1 1. And our polynomial is a 1 1. And you are appending a 1 0 only, because your n value is a 2. Two elements are there. Therefore n minus 1 0 bits I can able to append. So if our MSB is a 1, I am starting with a 1. So 1 1, 1 here, 0 here, and drop this. Again MSB is a 1, 1 1, 0 1, cancel this. This one you drop. Again your MSB is a 1, I can continue. 1 1, 0 0. Now this one you drop. 0. So as your MSB is a 0, so I can do with the 0 0, and your final your CRC is 0. Now this one the sender will transmit your data. How he is transmitting? 1 0 1 1, 0 is your CRC, and this is got received by receiver this way. 1 0 1 0 and 0 is your CRC with a polynomial 1 1. Now I have changed the bit position. So this bit instead of 1 is arrived at 0. Now let us cross check. So 1 1, as your MSB is a 1 1 1 1 1 0, cancel this, drop this one. Again MSB is a 1, so 1 1 0 0, cancel this 0, and this 0. Your MSB is a 0, I am doing with the 0 0 0, cancel this 0, again 0. Now as your MSB is a 1 0 here, so I am doing with the 0, now 0 0. Now you see that this bit is got corrupted. I am sending the data 1 0 1 1 with your CRC as your 0. If I do the cross calculation, is it able to detect errors or not, we want to get. So your data is 1011, polynomial is 11, and I have appended 10 here. So it is a 11, 0 is a cancel, again 1, 1, this 0 is a cancel, again this one, 0, 0, 0 is a cancel, again this one, 0, so I have transmitted like this, 1011, and the CRC is with 0, and receiver receives as 1010 with your CRC 0, and your polynomial is 11. So I'm starting with a 1 because your MSB is a 1, so it is a 1 1. So 1 and 0, the 0 you can cancel. As your MSB is a 1, I'm doing with a 1, 1 1, 0 0, cancel this 0, and this 0, 0 here, as 0 0, 0. Now you observe. So this is what? What is this? So if data is arrived as one zero 1 1, the sender side is happening. He has transmitted with the CRC 0 to us, and now this is transmitted to the receiver in such a way 1 0 0 0, and this is 0. Now again we are trying to do the same 1 0 0 and 0 with a 1 1, as your MSB is a 1, so double 1, then 1 here and a 0, 1 0, again 1, 1 1, 0 here, you drop this 0, again with a 1, 1 1, 0 and 1, as 1 0, we got 1 1 and 1. So we understand that error is there. So this is how I can able to say that this is a good polynomial generator. This is a good polynomial generator because it able to detect errors. But earlier one, if you take only x, it is not possible to detect any kind of errors. So this is how you need to see that whether it is a good polynomial or not. So according to that, there are few polynomials are given, the CRC 8 and 10, 12, 16. This right now we are using an HDLC frame, and this CRC 32 is used in Gradium and is used in other applications. So I already gave the applications of CRC 32. CRC 32 can detect any length of errors. According to that, we solve the previous problem. So our data is 100 100, and your degree is 3. So 3 zeros I am appending. So your generator is 1011. Let us start with the 1. 1011. Now you drop this 0. You start with 0 because MSB is a 0. Cancel this 0. Drop this 0. MSB is a 1. Cancel this 0. Drop this 0. As MSB is a 0, do with 0. And now you drop one more 0. And now again you start with 1011 because MSB is a 1. So this one more 0. 1011 is 101 and 0. So you got 101 replace into this. Therefore, your CRC is 100,100. This is your M of x plus your CRC is 101. This is at sender side. You do the same process at the receiver side. If no bits are corrupted, it is going to give you a syndrome 0. If any bits are corrupted, it is going to give you syndrome non-zero. Now let us see the other one, checksum. Checksum mainly used by IP and ICMP and DCP and UDP. It is based on one's complement addition. It detects any length of error. So, but only the thing is that it's a 16 bit. You cannot exceed more than 16 bits especially. So if your checksum value is more than that in CRC, you can have up to 32 bits, but in checksum your maximum limit is only 16 bits. You can able to place in your EDC. Let us say what is the process at sender side. So my data is a 7, 6, 12, 11. Then he is asking find the checksum. Add all of them, it's a 36, and 36 is your checksum. Checksum is nothing but a sum. You need to complement it. So once you got complement, you got checksum. Now sender will send data as 7, 6, 12, 11 and your negative value, that is minus 36. So when receiver receives 7, 6, 12, 11 and minus 36 will get 0 if at all no bits are corrupted. 7 arrived like 7, 6 arrived like 6, 12 arrived like 12, 11 arrived like 11. Then you go and see that 100% 0. Otherwise you are not going to get a 0. You are going to get a non-zero. Non-zero will give you, if this value 7, 6, 12, 11 minus 36, if it is not equal to 0, then there is an error. If it is equal to 0, then no error. So this you can do in a different style. That your data is a 7, 6, 12, 11, which is nothing but 36. Write 36 in binary. This is 36 in binary. I'm trying to wrap it to 4-bit combination because your data is only 4-bit only. Therefore, what is going to happen? So I'm taking into 4-bit. So 100, 100 is your sum. Now this is your 4-bit. This is going to be wrapped. When this is wrapped, you got 0, 1, 1, 0. This is nothing but a 6. And if you complement this, you will get as 1001, which is nothing but 9. Now what the sender is going to send is 36 plus 9 all together 45. The sender will send. It is nothing but 7, 6, 12, 11 and your checksum value is 9. If receiver receives that value 7, 6, 12, 11, 9, The entire sum is equal to 45. Write this 45 into binary and try to wrapping it to 4-bit combination 101101. So this is going to be wrapped. So 1111, this is nothing but a 15, and this one you complement, you are going to get 0. That means you got no errors. This is how you can able to do CRC calculation. So for example, if data is given like this, so this is your data 1 1 0 0 1 1 0 0, 8 bits. So you need to see that your CRC is also, your checksum is also going to be 8 bits only. So 1 0 1 0 1 0 1 0. Next 4 ones 4 0 1 1 double 0 double 0 double 1. This you can directly convert in the form of what, a decimal, and do it. What is the decimal value, what is the decimal value, what is the decimal value, and what is the decimal value, and do it and wrap up to 8 bits. Otherwise we can directly also do here ones complement addition. This is a 1 1 1 means it is a 2. 2 is nothing but I can write in the form of 1 0 0 here, 1 as a carry. So 1 1 2, 2 is nothing but 0 here, 1 is a carry. 3 3 is nothing but double 1, 1 is here, 1 is here. 1 1 2 is nothing but 2 here, 1 here. 3 is nothing but 1 here, 1 here. 1 2 3 4, 4 is nothing but 1 0 0. 4 0 dot drop it, and 1 0 is there. 1 0 is nothing but 2. So 2 plus 1 and 4, it is a 6. 6 is nothing but 1 1 0. This is your 6. 0 here, 1 1 is there. This 1 1 you add here, and your final value is how much? This is 0. 1 1 means 2 is nothing but 1 0. Carry here 1 1 0, and here you carry and 1. Rest is as it is 0 0 1 0 1. So total 8 bits you got exactly, they are wrapped. Now this is your sum. Now complement it. So after complemented, you got double 1 0 1 0 0 double 1. This is your sum. Now how sender will send? Sender will send all these 4 frames with your checksum value also. The complete frame will be transmitted. These are all will be transmitted just by embedding this checksum value. If any bits are corrupted, automatically it can able to detect it. For example, if receiver received in different formats 1100 1100, if receiver received some corrupted data, so identify the error. What is your data? 1100 1100, and 1010 1010. So both are pakka arrived. 4 ones 4 zeros. I have changed. This is wrongly arrived. And next one 11000011. This is correctly arrived. And your checksum also you please write 11010011. Now we need to calculate the sum. One one zero one zero zero double one. Yeah. So now you see that whether will it give you 0 or non-zero. You see that your value is supposed to be non-zero. If you get a non-zero, then we will understand that error, no doubt. If all bits are correctly arrived, then you are going to get a 0. So let us once cross check. So 1, 2, 3, nothing but 1 and 1. 3 is nothing but 1, 1. 2 is nothing but 1, 0. 4 is nothing but 1, 0, 0. So 1, 2, 3, 4, 5. 5 is nothing but 1, 0, 1. So 1 here and 1, 0, which is nothing but 2 here. So 2, 3, 4. 4 is nothing but 1, 0, 0. 2 here and 1, 0, which is nothing but 2. So 2, 3, 5. 5 is nothing but 1 here and 2 here. So 2, 1 plus 3. 3 is nothing but 1 here and 1 here. So 1, 1, 2. 2 is nothing but 0 here, 1 here. 1, 2, 3, 4. 4 is nothing but 1, 0, 0. 0 here and the rest 2 here. And 2 plus 4, 6. 6 is nothing but 1, 1, 0. 0 here and keep 1, 1 as your carry attached to this. Now you got 0 or not, you need to check. 0, 0, 0. So this is 0 and this is 0 and this is a 1. 1, 1, 0. So 1, 1, 0. Carry here, triple 1. 1 here, 1 here. So 1 here, 1 here, 1 here and 0. So this is your sum. Complement it. Once you complement, you're supposed to get 0. So 1, 1, 1, 1, 2, 3, 4, 1. So I can understand that there is a what? Error. So this is how the checksum is going to give you errors or not. So I have two questions to you. What is that? I said CRC can detect any kind of error, especially. Now my question is that can checksum detect any all kinds of errors or not? Can checksum detect any kind of error or not? This is my question. So you tell me, then you can understand that which is the best. Right now CRC is the best, which is using by CSMA and others, many of your applications, including your Ethernet also. Now one more task to you. So that is nothing but, so you solve these problems which are there. So this problem you solve using xq plus 1. So our polynomial, the CRC is supposed to be 3 bits. This is wrong and this is wrong because your message size is supposed to be your m of x and plus your CRC. As your CRC is a 3 bits and your m of x is a 8 bits, so your answer is supposed to be 11 bits code word. So you see that 11 bits code word is there or not. Okay, my dear friends, so this is one of your tasks. We also try to solve this task using the same. So here also 4 plus 4, 8 bits and your polynomial is 3. So your code word is also 11 bits. So you see that what is your answer in this. That's it, my dear friends. So this is how you can able to show the differentiation between CRC and checksum. So please see one important point you need to observe. CRC is a bit confused and bit difficult. Why? Because you need to generate CRC generator. This is very important. It completely depends on CRC generator only. So you need to see that whether it is a valid generator or not, and you need to see that whether it is a good generator or not. Good generator is nothing but which is going to detect what? Errors. Which is going to detect errors. So you want to say that it is a good generator or not. You see that your n value is supposed to be greater than is equal to at least 2. Your n is nothing but number of elements. Number of elements in CRC. So invalid CRC generator means your n is equal to 1. So if you say that n is equal to only one element, then it is called what? Invalid generator. Your CRC must have two elements at least or more than two elements. It's completely based on binary addition. That's it, my dear friends. So in the tomorrow's class, we are going to discuss about Hamming distance. Thank you very much. Please stay tuned to Unacademy. Immediately join in Unacademy using a referral code that is called SANKAR. Then you are going to get good amount of discount. Thank you very much. We'll meet in the tomorrow session.